Good morning, everybody, and thank you for showing up. We appreciate your participation. Let me get the screen sharing going. Cindy, do I have permission to share screen?
Yes, you should. Your codes.
Okay, great. All right, so I am Mary Thomas. I'm with the San Diego Supercomputing Center. Can you all see a slide, a web browser with Expanse on it?
Yes.
Okay, great. So I just wanted to take a moment to let you guys know, you probably already know our training page. We've got some other related events coming up, and I'll go over those after my talk. Today I'm going to talk about accessing and running jobs on the Expanse system or in general HPC systems. Can you see my slide there, the main slide?
Yes.
Okay, and I don't need to have this Zoom thing here. Okay, so that should be a clean view for you guys, right? Do you see my control bar?
No.
Okay, great. All right, so let me get the focus here. So I have a long outline and quite a few slides to make this talk complete, but we won't go into everything in great detail. It's just a lot of reference information, especially some hands-on examples of the different types of parallel programming models that we support, and just some hello world type examples for CPU and GPU. So without further ado, we'll just get going. This is a picture of Expanse. It's in my background. You can see it. I like to show it to people, especially for the audience that we target this presentation towards, which are people who might be new and not even programmers that write parallel code, but they're going to be using applications and projects that are already running on Expanse, like games or Amber, or you might be a programmer developing new code and migrating code to Expanse, but it's kind of a new environment for you. So I'll talk a little bit about Expanse, and just to give you some orientation, this long colored object is called a rack. And in the rack, you can see a lot of hardware components in it. And I'll talk about what they are. They're everything from CPU nodes to GPU nodes to storage right on each rack. The bright green colors show the cooling lines. This is a liquid cooling machine so that we can get more power into it and out of the system. And we have 27 of these racks, I believe, or let me get the count right, 13 racks. So this is a diagram, a drawing of the Expanse system. So that's one of the compute racks you just saw. And on each of those, these are called scalable compute units. They each have some compute nodes, some GPU nodes, and there's large memory nodes on some of the racks. The idea is to, for the scale of problems, we expect to be running on Expanse, which is sort of an average number, not a million cores, but thousands, tens of thousands of cores. We expect that you could get everything done on one of these racks, so you could reduce, message passing time and have more efficient and effective computing. Expanse is designed for what we call the long tail of science. Again, it's JAWS. They took a look a long time ago when they first designed the Comet machine and realized there's a tremendous number of compute problems that require HPC resources at large scale, large memory, for example, that don't use millions of cores, but they need thousands of cores. And so we've designed the systems for that usage group. And so they're not, so anyway, everything could be contained on one of these nodes. It's a data-centric architecture, so we have large storage and fast I/O, and I'll show you some diagrams of that. And then also some new experimental innovative features, composable systems, which is computing out on the edge, high throughput computing. We have a lot of science gateways, interactive computing, using notebooks in a more secure, safe, advanced way by default, making it natively usable, and containerized computing and cloud bursting. Some of these are research features that will be released over time. Expanse is a 5 to 10 year system. So borrowing briefly, if you want to know more about these, go to the Expanse webpage, and there's a lot of information in the user guide. But these scalable compute units, it's just a little diagram of how it has its own high-speed switch. It has these different nodes and chassis with nodes in them, and the GPU nodes. And so the system layout, you can see the picture behind me shows you this side of the system, multiple racks going through. There's a cooling system, there's airflow around it. We have high performance storage in the form of a 12 petabyte or greater Lustre file system. These numbers may have increased a bit since we're in our second to third year of operation, and we keep adding scalable compute units and other features. We have Ceph object storage and then the management rack, and we also have a high-speed network. This is a little diagram that shows you the connectivity fabric for a system like Expanse. If you're new to HPC, we have some other presentations that are for what we call the non-programmer community with basic parallel concepts and just what is all this hardware all about. But in a nutshell, it shows you here's Expanse, those big racks back there. Here's the storage connected through high-speed networks. You want the faster the network is, the faster your job will run. And then we have these data movers using Globus, and then 200 gigabit per second networks. We have high-speed networks off campus where we're connected to the Scenic network across California and other networks, the Pacific Research Platform networks. So it's highly connected, which should make it easier for you to move your data on and off of Expanse and on and off of the compute nodes on Expanse. I'll talk briefly about that. The next slide really just covers some of the basic skills that you need to know to work on Expanse. So we have Expanse 101, which this tutorial leads to, is a self-guided tutorial where you can go in and run jobs, run a little test to make sure you know how to use Expanse. We have a repository, GitHub repository. You do need to know how to use a GitHub repository, and that's one of our basic skills. So we're building up this repo so you can go in and say, I don't even know how to use Unix, and now I have to run a job on this, 20,000 core job on a machine that I don't know how to use. So we have a tutorial on that, and you can go in and go, for example, to basic Linux skills. It's done in what's called Markdown. So you can see a command and then cut and paste it and make that work over in a Linux web, in a terminal. So for example, to log on to Expanse, I alias command, so I'll show you my command. And so if I type Expanse, that command, that SSH, I'll talk about that, command will run, and if all goes well, I'll get logged on. And there seems to be a delay in getting logged on. So when that happens, I'll show you. Again, in this browser, we also have HPC security, and we have, so this is talking about about what does it mean to connect, what is SSH, what is SSH auth, which is our preferred way for you to connect, so you can do passwordless connection by forwarding credentials. And then notebook examples, we fully support notebooks, both serial, parallel, whatever you need to do. We have a lot. We're doing a talk on that, and Marty Candace did a talk in December about running secure notebooks on Expanse. So if you're using notebooks, and these days most people are, we have some demo ones that work are at Hello World or a little bit beyond Hello World. We're bringing in some parallel notebook material. Again, go back and see the December webinar. And somehow I am not, live demos are always dangerous
Mary,
to do sometimes. Yeah.
Yeah, just one note. Please try to log in directly to login 01. We have a memory issue on login 2, so that's probably why I was hanging.
Okay, thank you. Glad you're here. Okay, so I will type yes, something's there. So you can see even logging in can be a little bit sketchy, but I am now logged on and I'm in my home directory. So we'll get into some of that in the talk. So you can see that even for somebody like me that's been doing this for many, many years, surprising things can happen. So that's why we have a lot of examples of Hello Worlds and these kinds of presentations, so we can orient you guys on what it's like to run on these systems. So let me go back into, that's the last live demo for most of this talk. Okay, so logging on to Expanse. Again, you just saw, you need to have an Expanse account and you need to know how to log in and sometimes anticipating issues. It's great that you got to see that. And if you have a problem, people like Marty are waiting to help you on the Expense help desk. So I'll show you that link in a moment. So you need to have an account. You either have somebody who's a PI with an active project, they add you to their project. You can submit your own proposal. There's a couple different kinds of proposals. You can get a startup allocation or submit a full proposal. Startup allocations can be educational, like you're teaching a class, or it could be a way to migrate your code to Expanse. They're fast to get. They're much faster than the full proposal cycle. And they are intended for ramping up your work. You can get them for 1 to 3 years, but there are limits on how much the allocation is. But it's a way to get you on board so you can get your model running and see how it's going to run and will it scale and what do you need to do to make it scale. And if you want to request a trial account today, you can go to this link right here and follow the instructions to get a trial account on Expanse. It lasts about a month, but it's enough for you to get going. Expanse supports single sign-on through the Exceed user portal, or you can log in from the command line like you just saw me doing it. And you can also log on using the Expanse portal at portal.expanse.sdsc.edu. That's a very robust portal system that people are finding quite useful to get on and run jobs through the portal interface. It's important to note that CPU and GPU resources are allocated separately. So you've all seen this example, so I'm just going to move on for time. You want to use SSH keys to go between the two systems, and you want to make sure you have a good passphrase, and you can use SSH agent to forward your credential from your laptop onto the remote machine. This works for lots of machines, and it works by the fact that you have a username and password on the remote machine, and you log on and you intentionally copy and forward the key information to that remote machine. And you do that once, and then after that you have passwordless authentication. We have a couple of webinars on those, so you can go back and take a look at them. We have an updated revised security webinar coming up in April where Scott Sakai will cover that. System access, when you're logging in, the important thing to realize is that you're over here on your laptop like you saw me do it. I logged into some node, login 02.expanse.sdsc.edu today, and then some switch will route me around to my home directory. And when I want to run a job, I'll talk about that today, you submit a job to a server that then decides which of these nodes. I'm not going to pick node 2198. It will pick a node for me and then tell me what my nodes are and run my job. That's called a resource scheduler, and I'll talk briefly about that today. So then a terminal connection, you just saw that. Usually you get a welcome message with some MOTD. Using the login nodes, we want to make sure you realize the login nodes are just meant for you to log on, do a little bit of compiling, no running of parallel code. There's debug queues that have a quicker turnaround, so you can submit jobs to that. So MPI and things like that are turned off. There are some applications you can try to launch, but if we find them, we'll delete them. Like a Jupyter Notebook needs to be run on an interactive node. I'll talk about that. Don't use the login node for computationally intensive processes, running workflow management tools. You can don't use it as primary data transfer nodes. We have a data mover for that, like where you're moving a petabyte of data. Don't use it for hosting HTTP pages, and don't run Jupyter Notebooks. All of these things impact the thousands of people that might be logged on at the same time. You get on, you submit your job, and then you get that interactive node and let the job run or interact with your code that way. They're not the same as these batch nodes, the big compute nodes that are on that rack. Again, you can use the Expanse user portal to run all kinds of interactive services like notebooks, MATLAB, RStudio, and we'll go into some more of that a little bit later. Okay, so one of the most complex things when running on a supercomputer is what's my environment? who am I? How do I know what directory I'm in? What's even the date? What's the name of the host name? And those are all controlled by the shell environment. And seriously, if you don't know what I mean when I say a shell, you need to go back and learn basic Linux skills, spend a few weeks doing that. It'll be worth your time. And we have a training module for that will help reveal what you know and don't know. You have to be able to move around in directories in the Unix way, not the Windows way. So it's just a warning that if you get on there and you're really lost, it's not unusual, and we have training material to help you with that. And there's tons of online training material as well. So you need to be really comfortable with Unix and shells and scripting and running commands from the command line. So we set up these environments, and what we've moved towards is a customized user environment using modules. The modules allow you to create an environment for each of the applications you might want to run, depending on what you're doing. If you're testing and debugging, you may just want compilers and other specific libraries in the path. And if you're running an application that's already provided, like Amber, you wouldn't want that same compiling environment. So you can customize them and reload them at will. And I'll show you some examples. It takes a little while to wrap your head around the concept of modules. So go and read about the Lmod scheduler, Lmod environment that we're using to get a better feel. So you need to load a scheduler, for example, that resource scheduler that picks the nodes for you. We call it Slurm. You won't see all the some caveats. You won't see all the available modules when you run module available command, for example. Without loading a compiler, you won't see what compilers are available. But once you load that compiler, other software dependent on that particular compiler, and I'll explain what compilers we support in a moment, then they'll start showing up. So you build on a system of information, but you have to know how to build on that system of information. The way you do that is you can use something called the spider tool, and it will go look and show you what's available given the environment that you've got. You can look with keywords or just a package name that you might be looking for. Am I using Amber? Do I want to use an Intel compiler or a GNU compiler? So you can also use the package that you're looking for. And you can get more details on particular modules that you're looking at with this module spider application name. The module paths are different depending on whether you're on a CPU or a GPU machine. So don't load both. You're either going to work on a CPU or a GPU to start your job. And so that's the one that you want to load. There's certain commands that are popular. You want to list the modules. You want to know which ones are available to me. That response will change depending on which modules you've already loaded. It's a very dynamic system. So I think of the modules that you want to load for a particular task you're doing as a recipe. And you might want to save those recipes in little text files so you can remember, oh yeah, I'm running games. I want this set. I want to run a Jupyter Notebook. I need these modules. And you just keep building that information. So kind of try and get that habit to save ones you want to show your environment variables you're working with right now. You can remove a module and change it. You can load a single module. You can swap modules. For example, perhaps I need a particular Intel compiler and I have the wrong one in for my system. Then I swap the modules. And you can get help with the modules. And sometimes when you change one module, it affects all the other modules. The system will try to anticipate that and change them for you. You have to sort of track that. Just here's a simple example. I'm resetting the modules. I'm kind of cleaning up my environment. That's a good habit to have. I'm listing the modules that I had by default when I did the reset and when I logged on. I have CPU, I have Slurm, I have an Intel compiler. And I want to know which ones are available based on the environment I've got. And you can see this list. It can be very, very long, but I've got Abacus, Anaconda, CMake, GCC, all kinds of little pieces are in the modules. So you can do module show to tell you what a particular module does. Now this is CMake, it's very short. Sometimes they are pages long. It'll depend on the module. Once you've loaded the modules and you learn about it, you can check that these are the variables that you want to use. For example, in this example, it gave me my library path. And I made sure I'm getting the GNU compiler and I know exactly where it's located. So the modules are located on Expanse, but in different directories. So sometimes you get a command not found, or when you're building and changing and manipulating that module environment, things may change, and so it's a little confusing. So what you can do is you can just sort of reset things by running this modules.sh script. All right, so let's move on to account management. This is it's important to know what your account is. What's my user ID on this machine I'm going to, but also you have to have an allocation. You might be able to log on, but if you're out of allocations, you can't run anything. So you have to have allocations, and you might have access to multiple projects or accounts, and you need to know which allocation do you want to charge a particular project task to. So get to know that part. You should verify that you're using the right project. Awards are granted for specific purposes, and so don't abuse your access to an allocation. So to charge your job, you have to use either in the batch script, I'll show you what those look like, the project number here, or srun from the command line. You can get information about your allocation. You have to load this module provided by SDSC and run an application called the Expanse client. So here's an example, Expanse client, and then you get a list of all the projects and how many CPU hours I've used and what's available. And that's the overall aggregate usage. So in this example, ABC123, I've used 1596 out of the 3267835 SUs available. Okay, so remember to load the SDSC. So when you log on, you can first check it. Charging is like money. You get allocations and then you use it judiciously, because you don't always get as many hours allocated to you as you would like. The basic charge unit is a service unit for CPU. It's approximately 2 gigs of data for 1 hour. For GPU, 96 gigs of data for 1 hour. If you have questions about your job charging, send a question to the help desk at exceed.org. Shared partitions will be based either on the number of cores or fraction of memory, whichever is larger. So you can save CPU costs by sharing a node. Each node has 128 cores, and if you only have a 16-core job, you could share that node if you're not worried about controlling, like using all the memory. If you have smaller test jobs, and then let other jobs run on that node, they'll be sandboxed and protected, but it might impact performance. But if you're not worried about that, you're just trying to see if your code's running, then share and use that. It'll be cheaper. The minimum charge for any job is 1 SU. So if you ask for 20 SUs and you only 20 hours and you only use 1, and you don't turn that job off or kill it or delete it, you're going to get charged for 20 hours of running. So be aware of what you're asking for, how much you're going to use, and be sure to delete things if you're done with them. And there's more information in the user guide on that. And it can be a little complicated, so send questions, like I said, to the help desk. So the next thing you need to do if you're running jobs on the system is to compile code and get it to run right. There's a ton of compilers out there that we support on Expanse. GNU, Intel, AOCC. Expanse has the AMD nodes on it, and they have specific compilers. There's multiple MPI implementations, and we have OpenMPI, MVA Pitch, and Intel MPI. Majority of applications have been built using the GNU compiler, which features AMD ROM optimization flags. And the Intel and AOCC compilers support advanced vector extensions. One comment about the compiler is each compiler will have some different performance on the same system. And in one case for your application, the GNU compiler might perform faster, or the Intel or the AOCC. So if you're trying to optimize and get maximum performance, they should all get the same answer. They should all get the same result, but they might run differently, and you might want to test them out, and you might be surprised. So just a caveat on that. The CPU and GPUs have different compilers, and an Expanse login node is not the same as getting onto a GPU node, and the environment once you get on that GPU node is different, and the compilers will be, of course, different. So just a quick overview. These are all presented in greater detail in the user guide, and everything in this talk is based on information from the user guide, which is always going to have the most current and updated information. So there's different languages. Of course, we also support Java and Python. I'm just looking at the basic HPC languages. And so there's a serial version of the command, an MPI version, an OpenMP version, and a hybrid MPI plus OpenMP versions. And for each of the compilers, these are presented in the user guide and in this talk. So you have to load the compiler you want, and then you want to get more information on that compiler, and then run the compiler command to make sure that your code compiles. So using the AOCC compiler, I'm going to list my modules here. I'm going to first start over because that's an older application. So I'm going to purge my environment. And then I'm going to list. I have no modules in my environment. I'm going to load Slurm. I'm going to load the CPU module. I'm going to load the AOCC compiler. I want to use OpenMPI. And then now I'll list my new environment, and there's Slurm, CPU, AOCC, and OpenMPI. So the system did all of that for me. That's sort of my recipe for whichever application I'm looking on. But now I decided, no, I want to use Intel. And so I'm going to swap that with AOCC. That's a typo on that line. It should say Intel. I need to fix that slide. Make a note. Okay, so Intel compilers work the same way, but you'll notice the command for compiling is a little bit different for all cases. It depends on your language and the compiler you're using. This one we're loading MVA pitch. And then here's some examples of loading the Intel compiler. So there are some features on the Intel compiler you want to be sure you access, which is the vector extensions. Then here's how you do it. This gives you optimized file data movement in the core. And the Intel math kernel library is very, very popular. So if you want to use that, you want to make sure you have the right environment for that. And we have an example in our test codes, which I'll show you at the end of the talk. PGI compilers, those are very popular as well. And you might end up picking a compiler because that's the one you've inherited from your project, and that's fine. These all work very well on the system. So here's the examples here, and there's an example of loading the PGI compiler. And where's my compiler? This shows you some details on that. Notice they're all in a similar area, but they're all slightly different depending on how the installation goes. The user support people take care of all of that for you. You just have to type module load PGI. If you have some application and you need a customized specific library, reach out to the Exceed help desk to see if they can help you. Maybe it's already there. Maybe they want to install it for the system, or they can show you how to install it locally and access it. For GNU compilers, it's very similar. These are probably more familiar to everybody, but just make sure when you're running an environment and loading the libraries that you're loading all the GNU versions if you're working with GNU or Intel or AOCC. And here's an example of loading in a GNU environment. Notice I'm always purging, loading Slurm so I can run jobs, and then loading CPU, and then I get more customized. Okay, so for compiling, there's two kinds of jobs you can run. So just a little side note about memory. There's distributed memory and shared memory. And distributed memory means your jobs are running on discrete CPU resources, and that in order for the CPUs to share data, they have to go through some kind of remote interconnection network. And that's the MPI model. And also distributed services, SOA, web-based online games, peer-to-peer apps, and there's a lot of different distributed memory models. For us, we used MPI, message passing interface, to interconnect the nodes that would be sharing data. And it's optimized for every machine. But there's also shared memory models that work on HPC systems. So if you have 128 cores on one node, those cores can all share data. I didn't go into a great detail on the architecture of the EPIC processor that's used on Expanse. That you can look back at our webinar in January that Bob Sinkovitz gave, and other webinars last year that go into greater detail on Expanse architecture. But the shared memory means there's some local memory that they all have a really high speed interconnection access to, and the data is read and written to with a local, you don't have to do any message passing. So OpenMP, parallel threaded processes, those are shared memory. Okay, so now we want to learn about running jobs on Expanse. So you run jobs in the batch mode typically. You submit a job to be run on this system. You let the Slurm scheduler find the nodes that you need, 100, 200, 1,000. And then you have the code ready to be launched, and Slurm will launch your code on all of your nodes. And computationally intensive jobs should be run only on the compute nodes. Expanse has limits on the number of jobs you can queue up and run, and also limits on the number of jobs in a partition. If you submit a large number of jobs, especially short ones, it can impact the scheduler, and we don't advise that. If you feel like you need to do that, get some guidance from the help desk on how to set up that script to run the jobs efficiently and effectively. So you can run jobs using the Slurm scheduler, or in an interactive mode where you actually get a compute node, and you're logged on to the compute node, and you can run your code as though it's local, and that's interactive. So Slurm is you make a script, you submit the script to the Slurm scheduler, you tell it when you get my nodes, I need 100 nodes, and I need my job to run. It's going to run in 1 hour. And it will get 100 nodes and then launch your job onto all the nodes. And the jobs will have code inside of them that know how to coordinate and the interaction between the different processes running on the nodes. So those are Slurm jobs or batch jobs. And then the interactive jobs, these are the commands to get onto the CPU, and these are the commands to get on the GPU. Notice this account number, that's a fake account number. As XYZ123, you have to have a real account number. You'll get this command would be rejected if you tried to use that. So remember, this is fake, and put in a real job ID. I get emails from people who kind of get so busy they forget. So what's Slurm? What's this resource manager? The simple Linux utility for resource manager. It's sort of like a glue. It's a lot of services that are running, and its job is to take your request in the batch script that defines how much memory, how much time, how many nodes you need, the name of your code, other special features you need to set, and arguments you might want to pass to your code. And it will figure out what's the best set of nodes for you and when they'll be available. Sometimes on a busy day, you might wait quite a while. Or it could take a couple of days to get what you need. But then once Slurm can schedule in and anticipate and set up your job, you'll get a notification, you'll get a job ID, and you'll be told that the job is pending or running. I'll show you what that looks like in a second. But Slurm is a really complicated system and does its job very well. So you'll be interacting with the Slurm by submitting what we call a batch script, and it's got a particular scripting syntax. So partitions are really just the way the system is divided up and how jobs will run on it. There's compute and shared. There's GPU and CPU. GPU always has GPU prefix. There's shared, and there's something called the debug. Notice that these are very short jobs. They're short and quick, and they're intended just for testing and debugging. Is my script working? Is my code working? Before you go and wait for something longer. If you want to preempt, you should work with the staff to make sure you're setting that up correctly. To submit a job, there's common Slurm commands, sbatch, and the name of your batch script. I'll show you what those look like in just a second. You want to check, is your job running or not? In this case, the job is pending. After a while, who knows how long, it will be running. So you can see R for running, P for pending. And then once it's running, you can begin to expect to, if you're printing out debugged information, you would start seeing that output. If you aren't printing out anything intentional, then all the standard out from your code will get aggregated and collected by the Slurm system. And when your job ends, it will all be put into an output file. And you can control the location and name of that output file. But it can be very frustrating if you have a really long running job to not know what your job is doing. So you might want to put some debug IO statements in your code at the beginning when you're first testing it. Here's an example of a batch script. So we tend to use the extension .sb for Slurm batch. You can call it whatever you want. And this is a simple example that doesn't require any code. It just tells you what your compute environment is on the machine. And a few key things to notice is that this is in the bash shell. Again, if you don't know what I mean by bash shell, go back to basic Linux, and it's the environment that the computer sets up for me when I log on. In order for me to even log on, I need some kind of basic core environment. I choose to use the bash shell. There's other shell environments you can use. So in this script, if pound sbatch, that's a keyword that alerts the Slurm scheduler system, hey, anything that begins with pound sbatch, that's its job is to parse all this and then to build a job out of it. So I can set the name of the job, I can set the name of the output file, environment info, %J, %N, that'll give me the job ID and the node name that it's running on. And I haven't set a full path, so it would be in the directory where I launched the job from. Here I'm using the compute partition, 1 node, 1 task per node, 1 minute. This is a pretty fast code. And in it, I'm setting up my environment. We advise you to always set up your module environment, that little recipe to control the environment, to make sure you get exactly what you need for your job to run. Because in Unix, when you start running jobs and launching processes and even typing a command, all kinds of shell environments get set up. And if you don't set those, you might not get what you expect during the job. So get in the habit then of putting that little recipe in here. And I'm just going to perform some basic Unix commands like, what's the host name? What's the date? Who am I? What's my username? What directory am I in? What are my modules? And what's my shell environment? And here's the output. Here's the name of, this is the name I put here, %J, that's my job ID, and %N, that's the node it was on, and .out. So I've made that name right here. And so the host name, I'm not on the login node. That is the name of the compute host that the job ran on. Here's the date, I'm M. Thomas. I'm in the working directory. That's where I submitted the job from. Here's my modules. And then the environment can be 90 lines long. It can be quite long. So I just snip means I've removed content. That's the most basic example. And this is in an example repo that you can access and get the code from and run it yourself. It's always nice to have something that if it runs, you know you've logged on, you can run a job, scripting works for you. You can test so much of your current environment just with this simple script, which is why I put it in there. It's kind of pre-hello world. So you have to be aware of where you're running your jobs from. I don't have time today to go into large detail about the file system. There was a webinar presented, I've got it down here, back in October, that goes into great detail. The file systems can be very complicated. What from today is there are 3 directories. There are 3 main file systems where you work. When you log on and you're in your home directory, your high-speed data, large-scale data system is the Lustre file system. And when you get assigned an interactive node, you have local node file space. What you need to remember is that this is temporary. You only own that file space while you're running your job. So if you have data on that node before your batch script ends, you need to move that data back either to your home directory or onto the Lustre file system, which is where every user has their own space to store data. And you can, yeah, so you can move your data around and check out this webinar. So for the Lustre file system, it's 12 petabytes Ceph object storage, high-speed access. You should be able to access it from all the compute and GPU nodes. If you have a problem, get in touch with the help desk. Everybody's given a default location, and there's an NSF file system as well. It's best for scalable large block I/O. It's not good for a large number of small files. And this is becoming, it's highlighted in red because with machine learning becoming so pervasive, everybody's working on it. It has a lot of small, it can have a lot of small files, and small file I/O is really crippling activity on these HPC systems. So if you're having a lot of small files, please get in touch with the consulting team to make sure you're optimizing how you're moving those files in and out. We want you to do your work, but there are times when it can crash the file system. So please consult with us and get some input and some help getting that set up correctly. Scratch again is on the node where you're logged on to, and again, it's temporary. So it's, you have that available while your job is running. And in some cases, that's where you need to be doing I/O so that things are faster on that local node. But remember, in that batch script I showed you at the very end, before that ends, because when that ends, that shuts down all your access to the nodes. Make sure you're moving your data back into your Lustre Scratch system, for example. Globus endpoints, data movers, and mount points. This is what we want you to use for really large file systems. It takes a little bit of learning, and there's documentation online, but it's a high-speed way to move your data in and out. And there's more detail on that in the webinar that was given last October. But it's basically, there's different servers. You have an endpoint, that's basically you. You can do this through a web browser and set it up to move it from Expanse to what, let's say you have a local data server in your lab. And Globus then manages all the back-end connectivity, and it does third-party file transfer. You just say, Globus, here's my two endpoints, my laptop or my lab and Expanse. Move my data before, when the job is done, move it back. And then you're out of the process, out of the loop. It happens asynchronously in the background for you, and it's optimized and very efficient. So get to know using the data movers. And if you have questions, again, talk to user support. Good, so now we're looking at some specific examples, hands-on examples. So we have a repository, we have a training repository with some examples in it, and I have moved them also into another folder repository that I'll give you a link to. So you want to clone the examples from somewhere, and there's many places where you can find it. And then we have examples for CPU and GPU. The general steps to compile and run a job is go into your working directory, and for example, in the Expanse 101 repository into the MPI examples. This changes depending on what you're doing. Verify you've got the right modules. If not, correct them. Have your little recipe ready. Compile the code. For example, this is hello MPI F90, and have the output named hello MPI, and then verify that it's been created. It doesn't always work. And then submit your batch script, hello MPI slurm.sb. Let's see, I think I went the wrong direction. So we're in the MPI directory. This is a basic MPI stub. If you've never seen it and you're not going to program in parallel code, don't worry about it. But this is a Fortran. This is including a library that knows about MPI. I initialize the MPI system. A lot happens in this one line. If I have 100 nodes and 128 cores per node, that's a good sized job. It might take a few seconds to do that. But MPI init gets the your code, hello MPI, on all of those nodes, sets up the environment. The nodes set up an interconnection communication protocol. A lot goes on. And then I can tell how big is this MPI-Com world is kind of the name of that group. And then I get my number in it, sort of like my address on the street of the 100 nodes that are going to run hello MPI. And I print out my node and my rank, hello world, and then I shut it down so that the system can clean it up, and then I exit. So here's README files. In our examples, we try to include a README that tells you what the recipe should be. Caveat, that's what worked the day I ran it. Sometimes things change, so you need to make sure you have an environment. We try to keep these updated and current. It tells you the command to compile, how to submit, and then how to run it on an interactive node as well. And so here's my environment. I submit the job, and when I submit the job over here, I get a job ID. I'm queuing, checking the partition to find out if it's running, it's pending, and then it runs, and I get a hello.out file, and it prints hello world from the node ID. And this one had a lot of cores in it, so there's a lot of output. That's kind of what you'll see, the pattern you'll see for all of our examples. And I know that there's people answering questions, and I'll leave a moment or two for other questions. So we have hello world in as many versions as we can think of. Running it on an interactive node is a little bit different. Here, oops, here you'll notice I am on the login node, login number 2. There's multiple login nodes so that we can spread the load of all these people who are on. And I'm going to request a node for 30 minutes. And I wait a little bit. Sometimes you wait a long time, but I can tell I'm on the node because it's not login 2. I'm on Expanse-9-55. I set my environment, and then I run my hello MPI, and I get my output. And in this case, the node is really a thread on that node. Okay, GPU CUDA. GPU is a little bit different. Again, it's physically completely different hardware. So when you log on, you need a GPU environment. And right now we have NVIDIA V100s. I think it will be getting A100s. We have 52 nodes at the day this was made. I think it might be more. If you haven't done GPU, we do have some tutorials from the last couple of years on GPU computing on Expanse. So you can go look at that or just go out online. They're allocated as a separate resource. So because you're in my training class, oh no, if you were in our training class, we would give you allocations on both CPU and GPU. But if you want to work on CPU and GPU, you need to ask for both. And you can, there's startup allocations that will get both for you. And the login nodes are not the same. They're different environments. So again, you need to define whether you're going to run on a GPU node or not. And if you want it to be what the partition would be, GPU or shared. And here's how to get an interactive GPU node. You might wonder, why would I want interactive on GPU or CPU? Maybe you're doing visualization of remote petabyte data sets, or you're running MATLAB or RStudio or a Jupyter Notebook. That's when you would want interactivity. This is an example of being on an interactive node and looking at a Laplacian operation. And so here's the srun, so I can do it on the interactive node. If you want to know if you're on a GPU node, like let's say you have some code that's very dynamic and has coupled modules that do different things, and you want to, how do I check if I'm on a CUDA, a GPU node? You would run NVIDIA-SMI and get back real information. If you're not on a GPU node, that won't work, or it would bring back no information. So here I'm on an interactive node example here. I've loaded my modules. I'm compiling a Laplacian application, and then I get some output. Now for this example, there's a lot of output that you can just ignore it. And then we can run this job, submitting it to the GPU shared batch. And this is the batch script. Looks very similar. They don't look any different. Again, remember, change that account number, load in the modules, and then I can run the job on the GPU node, just the name of the job. And here it's running, it's waiting, it starts to run, and then I get some output from this Laplacian application. And that's the end of my talk. So some resources. We have a user guide. We have a training hands-on tutorial for Expanse. We have repositories in training-org for Expanse and a lot of other training material. And we have our training events and links to past events. And Exceed has training material as well. So I'm going to end the show and thank everybody for your attention. Hope you found this useful.